Alright, now that we've taken a look at what friction is and how we can calculate it, what we're going to do is we're going to go ahead and take a look at several example problems of how we could apply the concept of friction to solving a problem. And so the first one is a conceptual example where we're going to be solving using only variables, which means that when we get an answer, it won't be a numerical answer, but we should be able to compare the two in order to give it a correct answer. Alright, so Benny wants a ride on his sled. And if we're on flat ground, you have to decide, will you exert less force if you push him or if you pull him? And there are a few things that we need to do in order to make an equivalence here. Alright, in this situation, you've got a sled, then this would be the push, and here, this would be the pull. In order for these two situations to be equivalent, what we're going to have to do is we're going to have to assume that the angle here is the same as the angle here. Alright, so we have to decide under which situation would the friction be less. And so the only thing to do is to go ahead and take a look at what forces are acting on this situation. In this situation, your force would be downward, and in this situation, your force would be upward. So if we want to know which one is easier, the first thing you might think is well, in which situation is the Fx of your force going to be greater? But we know that if the angle is the same, the x component should likewise be the same. So let's take a look at a free body diagram of this situation. Right, in this situation, your force is a downward force, and the sled is experiencing a normal force, a force due to gravity, and friction. And in this situation, your force is an upward force. The sled experiences a normal force, weight, and friction. Just a quick warning, when I look at my two free body diagrams, I know that my vectors aren't necessarily all to scale. But I also know that in this situation that these are the forces that are present. If I set an axis on this problem, the simplest axis definitely seems to be the one that has 3 of the 4 forces along it. And that means that I would have to look at the components in order to solve this problem to figure out under which circumstance would the force be less. So here, I look in the y direction. I know that the y direction is experiencing uniform motion. Right? I'm not accelerating Benny upward or downward. And the same should be true over here. The forces in the y direction should be equal to 0. So why is that important? Well, the forces in the y direction are made up of the normal force minus the weight of the object minus here we can see the y component of the applied force. And that equals 0. And here you see the opposite, that the sum of the y forces is going to be equal to the normal force plus the y component of the applied force minus the weight. But in that situation, it still equals 0. So both of these are true so far, and we can see that the major difference here is the direction in which your applied force is acting in the y direction, because the sum of these forces under both of these circumstances should be equal to 0. Well, why does it matter? Well, it matters because in the x direction, you end up with your applied force in the x direction minus the force of friction in the x direction equaling mass times acceleration. And that's exactly the same in both problems. Well, here you might want to ask yourself, well, then how on earth could I tell the difference? Because in both circumstances, it's going to be the difference between the two forces that end up being the reason or the cause for the acceleration, because it's the sum of the forces. But may I remind you that the force of friction under this situation is going to be sliding friction, and that force is going to be equal to the coefficient times the normal force. And here is where it matters, because you see in both of these descriptions I can already tell conceptually that the normal force is going to be different, because the normal force is either balancing weight and the y force, or the normal force and the y force are balancing gravity. A simpler way to look at it would be to solve these two equations for the normal force. Under this situation, the normal force is going to be equal to the weight plus the y component of the applied force. And under this situation, the normal force is going to be equal to the weight minus the y component. And here I can see, in this situation, the normal force is bigger than this situation, right? And a larger normal force plugged into the exact same equation with the exact same coefficient of kinetic friction means that the force of friction will be larger in this situation and smaller here, right? Because here the force of friction is going to be equal to coefficient of kinetic friction times the sum of mg and Fa sine theta. And over here, the force of friction is going to be equal to the coefficient times weight minus Fa sine theta. If the weight's the same in both situations, the applied force is the same in both situations, and the angle is different in the same situations, that means that this is a larger friction, because you're pushing down or adding to the applied force to the ground that results in the normal force. And here you're actually pushing up, pulling up. So some of that force is actually reducing the normal force, making it easier to pull Benny. So that's a really great example of showing the value of friction in symbols. But sometimes it's helpful to just take a look at a numerical problem. And so we're going to take a look at a problem where we're actually pulling against friction. And there are a few things that are going to be the same as we've always experienced here. We are still looking at the mystery box full of scorpions. You are pulling it across the table at an angle of 30 degrees, and you're pulling it with a 40 Newton force. All right, so the weight of the box is still going to be 10 kilograms times 9.8 meters per second, or 98 newtons. The normal force is still going to be a result of this situation, and the only thing that's different is now we have the force of friction. Now remember, that's not a free body diagram, this is. And I would set my axis immediately so that it was along the majority of the forces. And setting my axis should prompt me to figure out what the sum of my forces in the x and the y direction are. And I should also think, if I'm pulling this box across the table, can I make a declaration about what type of motion? I can. In the y direction, I'm going to be experiencing uniform motion from a sum of the forces is 0. In the x direction, I'm going to be experiencing an acceleration of some sort. So that being said, I can say that the sum of the y forces is going to be equal to the normal force plus the y component of the applied force minus the weight of the box, and that should equal 0. Here in the x direction, I get that the applied force in the x direction minus the force of friction is going to equal some sort of acceleration. Now, a few things that I know about the situation. I know what the weight of the box is. I know that it's 98 newtons. I know the angle for the applied force is 30 degrees, so I'm going to go ahead and I'm going to actually write in those components where the force of the pull in the x direction is going to be 40 newtons times cosine of 30, and the force of the pull in the y direction is going to be 40 newtons times sine of 30. So I can plug those in. And I also know, finally, that the force of friction is going to be the coefficient of friction times the normal force. So I know if I'm going to solve for that mass times acceleration, I need to know the normal force. I grab up this equation here and I said that the normal force is going to be equal to the weight of the object minus the 40 newtons times the sine of 30. And since I know that the weight of the object is 98.0 newtons, minus 40 sine 30 is going to be 20 newtons. So I know the normal force is going to be 78 newtons. And since the force of friction is equal to the coefficient of friction times the normal force, it's going to be equal to 0.30 times 78.0 newtons, or 23.4 newtons. Here I can solve. The applied force is going to be 40 newtons times cosine of 30 minus 23.4 newtons, and that'll equal the mass times the acceleration. So I get 34.6 newtons minus 23.4 newtons, and that should equal mass times acceleration. Which means that I get 11.2 newtons, equaling a mass times acceleration. The mass is 10 kilograms, so I divide both sides by 10 kilograms, and I get the acceleration of 1.1 meters per second squared. Hate it when I do that, guys. So taking a look again, solving for the x direction using the force of friction that we just resolved. Fx applied is going to be 40 newtons times cosine 30 minus the force of friction, which is 23.4 newtons, and that'll equal mass times acceleration. So 34.6 newtons minus 23.4 newtons equals mass times acceleration. Resolve for acceleration with a 10 kilogram box, and I get 1.1 meter per second. You're going to notice that I reported to two significant figures, and that's because our limiting significant figure in this problem was the coefficient of kinetic friction. And so we want to keep this accurate to the correct number of significant figures. And last but not least, in our demolition demonstration derby, is two boxes on a pulley. We know that box B is accelerating downward, box A is accelerating to the right. We know that if we can assume that this string with this tension is massless, or we can ignore its mass, so we can ignore the force of gravity on it, and we can assume that this pulley is frictionless, then we know that the tension here is equal to the tension here, and that the acceleration of the box A should equal the acceleration of the box B. So we know we have two objects, two systems, so we want two free body diagrams. Box A happens to be experiencing the force of tension to the right, the normal force up, the box's weight down, and a force of friction that is a sliding friction that opposes the motion, which we said was accelerating to the right. We know that that box then has two components of acceleration, where we make this our x-axis and this our y-axis. Alright, in the y direction there is no acceleration. The box is experiencing uniform motion, so Fn minus mg is going to be equal to 0. In the x direction, we already said the box is accelerating to the right, so we know that the sum of these forces is going to be equal to mass times acceleration. So Ft minus the force of friction is going to be equal to mass times acceleration. And that acceleration is to the right, so we can assume that it is in the positive direction. Box B only has two forces acting on it, the force of tension and the box's weight. We were also told that the box is accelerating downward, so when we resolve these forces in the y direction, we know that the force of tension minus the weight of the box is going to result in an acceleration, and that acceleration is going to be in the downward direction, so that's going to be negative ma. Now, I have two unknowns. Those unknowns are the tension and the acceleration, and I know I'm going to need a system of equations, so it's going to be very important for me to distinguish between box A and box B. So here for box A, I'm going to call my masses of box A. Here for box B, I'm going to call my masses the masses for box B. Now, there's two things that I need to resolve for here. The first one that I need to resolve for is I need to resolve for tension. Right? The force of tension over here is going to be equal to the mass of box B times the acceleration due to gravity minus the mass of box B times acceleration. And I can plug this Ft in for this Ft because the magnitude of these two forces of tension are going to be the same. And so I do just that. I say that the mass of box B times gravity minus the mass of box B times acceleration minus the force of friction is going to be equal to the mass of box A times acceleration. I have yet another unknown though, because I have to solve for the force of friction. Right? The force of friction is going to be equal to the coefficient of friction times the normal force, which I must look into the y equation for. So I know that the normal force is going to be equal to the mass of box A times g. So when I plug it into the equation, I get that the mass of box B times g minus the mass of box B times A minus the coefficient of kinetic friction times the mass of box A times g will equal the mass of box A times A. So now, by substituting in the equation for friction instead of friction, tension for tension, and mass of box A times gravity for the normal force, I have reduced my problem down to nothing but masses and accelerations of gravity, and so I can resolve this equation for acceleration. All I have to do is do a little bit of cleanup or reorganization. So I need to get all of my accelerations on the same side. So mbg minus mu k times mag is going to equal ma plus mb times a. And I solve this equation for acceleration, and I get mb g minus mu k mag all over ma plus mb. Now, this is a beautifully solved equation in terms of acceleration. This is the value of our acceleration. If we have numbers, we can now plug them in to resolve. If we don't have numbers, then the best thing to do would be to factor out the acceleration due to gravity and to present the equation as such. But now we have 9.8 meters per second squared times mass of object B is 2.0 kilograms minus 0.20, the coefficient of friction, times the mass of box A, 5.0 kilograms, all over the sum of box A and box B, which is 7.0 kilograms. And so my problem ends up being 2 minus 0.2 times 5. So that's 1 times 9.8 meters per second squared. So I get 9.8 meters per second squared times kilograms divided by 7 kilograms. And that ends up being 1.4 meters per second squared. So this problem was a great example of solving using variables and plugging in at the last minute. And it also shows how when you do a substitution for each unknown variable, you can solve one variable. And now, if I needed to know the force of tension in the rope and whether or not the friction has changed it, I can take a look now using the fact that the force of tension minus the force of friction is going to equal the mass of box A times acceleration. So the mass of box A is 5 kilograms. The acceleration is 1.4 meters per second. So that means that Ft minus Fr is going to be equal 7.0 newtons. And the force of friction is going to be 0.2 times 5 times 9.8. So the force of friction is 9.8, which means that the force of tension has to be 16.8 newtons. And so here you notice that once you solve for your one variable, you can choose the simplest equation to solve for the next. Alright, that does it for our example problems involving friction. Our next lecture will be example problems involving inclines, and then you're going to be on to your lab.